Okay, for the next part, let's take a look at an example question. In this question, we're asked to calculate the atomic packing factor for crystalline nickel. And as we recall, the atomic packing factor is an assessment of the volumes due to atoms in a unit cell relative to the volume of that unit cell. So take a minute to think about this question. And if you want, pause the video and resume once you've had a chance to answer it. If you're stuck not knowing how, a couple of pointers to think about are, we recall that the atomic packing factor is equal to the number of atoms times the volume of one atom Usually our strategy is to try to express the volume of an atom in terms of edge lengths. And then, of course, we want to divide through by the volume of the unit cell. And that's where our edge length parameter, typically A, will be found. To settle on what unit cell we're dealing with, you're going to have to consult a resource to determine what type of crystal structure does nickel like to pack into. Okay, so pause the video and see if you can tackle that, and resume the video once you've got an answer. Okay, so perhaps you flipped back to the earlier video, or you maybe saw that in this slideshow. We've got the earlier resource for us that describes many elements in the periodic table and their crystal structure. And so we'll see here that nickel, shown about midway down the chart, is shown to pack with a face-centered cubic crystal structure, and so that can be useful for us. So the face-centered cubic crystal structure, of course, has edge lengths A, and we have an atom at the face, and we contact through the diagonal, as such. And so there's a radius here. There are two radii there, and then a final radii here. The diagram doesn't really show that to a nice scale, unfortunately. And of course, that same kind of drawing could occur on each of the six faces of the face-centered cubic lattice. So we know that the total number of atoms is going to be equal to 8 corners times an eighth of an atom at each corner, plus accounting for those at the faces of each of the six faces of the cube. So plus 6 times, and as you might recall, we have an eighth of an atom at each, or a half an atom at each face, so plus that. So total number of atoms, the first part of our numerator in the APF equation, is going to be 1 plus 3, which is going to be 4. The harder part here is now going to be to express the volume of the atom in terms of edge length unit A. We can apply Pythagoras' theorem to help us. So we know that a squared plus a squared is equal to the hypotenuse squared, and that appears to be 4r all squared. So this simplifies to 2a squared is equal to 16r squared. And solving for r so that we can express the volume equation not in radii but in edge lengths instead, r is going to equal a squared by 8 r squared equals a squared by 8, and r is therefore equal to a divided by root 8, which is of course equal to A over 2 root 2. Okay? And now we know the volume of an atom is of course 4/3 pi r cubed. And so that's going to be 4/3 pi, and then substitute in r, A all over 2 root 2 cubed. And then we're tasked with simplifying this a little further. So a bit of algebra here to simplify this to make our job a little easier later. So this will turn into 4/3 pi A cubed over 8 to the 2 raised to the 3 over 2. And that can simplify down to 4 pi A cubed over 3 times 8 root 8. The numerator 4 here from 4/3 can cancel the 8, provided we leave behind a 2. And we can end up with a more simplified version of this, ultimately, that is pi A cubed divided by 12 root 2. Okay. Finally, taking all of that to our APF equation, we have 4 atoms times pi A cubed over 12 root 2 divided by the volume of the unit cell, A times A times A divided by A cubed. So that sets up a cancellation of that numerator and that denominator. And this simplifies down to pi divided by 3 root 2, which ultimately equals to about 0.74. So the atomic packing factor for crystalline nickel, which as you can see here represents all FCC lattices, is 0.74. Okay, an extra diagram here if you were struggling with the earlier concept that there are 4 radii. Down here are 2R and R. A little bit easier to see that there. Okay, so you see here that we've used some edge length concepts and some arithmetic, taking advantage of what we know about where contact points are to help us with calculations for volume, say for example in the FCC example here, to give us some tools to help us with APF calculations. And so I invite you to try to prove to yourself that this correlation here is in fact correct from your textbook, that the edge length is also equal to 4 radii divided by root 3. Okay, so that is, consider the slightly more difficult version here, where now we have contact points through the opposite corners of the cube here. So the contact points are all the way through the cube this time, not along the face. So you'll have to apply Pythagoras' theorem essentially twice to get to that correlation. Okay, and then let's lastly think a little bit about what we know about just matter in general. We opened the course with the idea that their bonding had implications on melt point and boil points, And so, as you know, metals can melt as well. So here's nickel. We just did a bit of an analysis on its FCC lattice. And so at a given pressure of around 1 atmosphere, we might start somewhere at room temperature here of around 300 K or so. And then as we warm the material, we'd eventually take solid nickel and pass it into its liquid state. So we would cross the phase boundary for solid nickel and cross into its liquid state. Okay, so as you might know, once we transition from solid to liquid, we move the matter from an ordered crystalline state into a more disordered state, where the atoms are scrambled in those 3 dimensions. Sometimes these disordered states are called amorphous or glass. So the amorphous nickel glass is shown at right, whereas the crystalline nickel compound is shown at left. It's curious to think about pressure if you haven't thought about that before. If you imagine we maintain pressure for this exercise of melting nickel at around atmospheric pressure, we would in fact liquefy the nickel from its solid state at about 1455 degrees C. And if you imagine keeping it at that temperature and now increasing the pressure and crossing back, maintaining constant temperature this time, you could actually solidify by applying pressure. So recall, the idea of applying pressure is like pushing on all 3 dimensions of the matter. And this might help you realize that you are now applying enough kind of force to help reorganize the structure, and you would crystallize back with enough pressure. Okay, so you could go to that earlier resource we saw a moment ago, and we can see here that the density of nickel is about 8.9 grams per cubic centimeter. Okay, so here's that value there. And you can see here that glassy nickel is less dense by the following factor. Okay, so there's about 0.636 to 0.74 as a ratio. Hopefully this number is now looking a little familiar to you. We just calculated that a moment ago. That is the atomic packing factor for crystalline nickel. So if we know the value of the ratio here as we consider the disordered nickel, 0.636, we can simply ask the question, what's the density of the glassy amorphous nickel, the disordered nickel? And so it's going to be equivalent by this ratio. Okay, so the density, sometimes given symbol rho, of glassy nickel is going to equal 0.636 over 0.74. That's the ratio, the information that's been given to us, times the density information of 8.90 grams per centimeter cubed. And so here you can see that we're going to end up with a number less than 1 here. So 0.636 divided by 0.74 times the 8.9. So the new density, the amorphous glassy nickel, is 7.65 grams per cubic centimeter. And in fact, less dense. So there are less atoms per unit space in the amorphous nickel. You already knew that if we recall the atomic packing factor information of 0.74. So we also know that in the equivalent unit cell volume, that now only 0.636 equivalent volume units are occupied by atoms. So 63.6% of the volume is occupied by atoms versus the 74% volume of the unit cell in the crystalline form that is occupied by atoms. Okay. So hopefully you feel quite comfortable answering a question like this. How many atoms of glassy nickel are there in an equivalent volume for the unit cell of nickel If we recall the unit cell for the FCC lattice and the total number of atoms in that. So for FCC, remember we had atoms at an eighth of an atom at each of the corners to give us 1. Then we had a half at each face to give us the total of 3. So that's the importance of the number 4 that we see in some of these answers. And so the options are A, we have more than 4 in the glassy disordered nickel, less than 4 in the glassy disordered nickel. Same for both, or perhaps you're totally confused. So take a minute to answer this question and resume the video once you've had an answer. Okay, so hopefully the picture and some of the numbers that we discussed on the previous slide helped you. We know that this, in the crystalline format, was filled with 74% of its volume with atoms, and we saw that it was more along the lines of 63% of the space filled in the glassy. So we have to have less atoms per unit volume, and so that's where we're going to answer B here for our answer. Okay, so hopefully some of those examples helped you put some of your knowledge to practice, and we'll see you next time.